Hey, you guys, in this section, we're going to be talking about logarithmic functions. Okay, so let's look at this. So the question that they ask us is, can we find the inverse function of f of x equals 2 to the x? So in our previous section, we know that 2 to the x, that is an exponential function. Okay, and we can tell that because the power, the variable is in the power, which is the exponent. Okay, so if you guys recall, when we talked about inverse functions, we followed some simple steps. So if they asked us to find the inverse, the first thing that we did, we interchanged the variables. So we substituted, instead of having f of x, we had it equal y. So we have y equals 2 to the x. We interchanged the variables. So where there was a y, we now see an x. And now we have 2 to the y. And then the next thing we would need to do is solve for y, okay? So as you notice, y is here in the exponent, okay? And we know from when we just looked at exponential functions, the only way you can solve for a variable that's in the exponent, the only rule we have right now is if we have a to the u equals a to the v, then u equals v, which means the only way that that power can come down is if we can get the bases to be the same on both sides. Well, the base on the left-hand side of our equation is x, but the base on the right-hand side is 2. So right now, there's nothing we can do to get those bases the same so that we can use the rule that we learned about previously, okay? This is why we need the logarithm, okay? The logarithm is going to allow us to solve this type of problem, okay? So by definition, okay, the logarithmic function with base a, where a is greater than 0 and a does not equal 1, is denoted by y equals log base a of x, and is defined by y equals log base a of x if and only if x equals a to the y. The domain of the logarithmic function y equals log base a of x is greater than 0, okay? So if you guys remember when we talked about inverse functions, okay, we just talked about exponential functions, okay? The inverse of an exponential function is a logarithmic function, okay? That's the relationship that they share, okay? Now, we also learned when we talked about inverses, okay, is that inverse functions share the same domains and ranges. They're just flip-flopped. So when we learned about exponential functions, we learned that their domains are negative infinity to positive infinity, all real numbers. For the logarithmic function, we just read that their domain is x is greater than 0. So 0 to positive infinity. So because these two functions are inverses of each other, okay, we know that then that the range of the exponential is 0 to positive infinity, and the range for the logarithmic is all real numbers then. They share this cross section between the two because they are inverses, okay? So in the previous section, we talked about the properties of the exponential function. In this section, you will see that those properties are going to be reversed for the logarithmic function because they are inverses of each other, okay? All right. So you're going to do a lot of work where you're going to be converting functions that are written in logarithmic form and then switching them to exponential and back and forth. So depending on what you're trying to do, sometimes your problem is easier to solve depending on which form that it's in. So sometimes it's easier if your expression is written in logarithmic form, and sometimes it's easier if it's written in exponential form. So you'll have to know how to convert back and forth between the two, okay? This first form here, okay, that's logarithmic form, okay? You can tell it's in logarithm form because it will actually have the word log in it, L-O-G, okay? Exponential form, what we've looked at before, your variable is going to be in the exponent, okay? Now, regardless of what form you're in, a is always called the base, okay? So you don't have to learn a new terminology for what a is. Regardless, in both log form and exponential form, a is always the base, okay? So we're going to practice converting from one form to another. So remember, if you're asked to put your problem in log form, it needs to look like this first one. And if you're asked to put in exponential form, it needs to look like the second one, okay? So let's practice. So these examples say change each exponential statement to an equivalent statement involving a logarithm. So for A, we have 1.2 to the third power equals m. Okay. So if we want to write it in log form, let me copy these down here for you guys so you can see. All right, there we go. Okay, so right now we are in an exponential form. So that means our base for our problem, which would be a, is 1.2. Our exponent is 3, and our x is m. So if we want to write it in log form, we would say log base 1.2 of m equals 3. Okay. All right, let's do b. B, we have e to the b power equals 9. So in log form, we would say log base e of 9 equals b. That's it in logarithmic form. And let's do c. So c is a to the 4th equals 24. So in log form, it would be log base a of 24 equals 4. Okay? So if you need to, for each problem, you can label what the a is, what the x is, and what the y is. Okay? So let's actually do that so you guys can see it. Okay, so for a, okay, our base was 1.2. All right, our x was m, and our y was 3. Okay, for b, our a, or our base was e. Our x was 9, and our y was b. Okay, and for c, our base was a. Okay, our x was 24, and our y was 4. Okay, so if it helps you to label those parts so that you can put them in the correct form, go ahead and do that, whatever makes it easier for you. Okay. All right, so in these problems, we went from exponential form to logarithmic form. Let's look at a second set of examples where we're going to go in the reverse order. Okay. So these say change each logarithmic statement to an equivalent statement involving an exponent. So this time we're going from log form to exponential form. Okay. So let me write the rules for you again. All right, and a to the y equals x. All right, so remember, those are our two forms. So let's do a. Oops, shift it over. Okay, so we have log base a of 4 equals 5. Okay, so if your statements are written in logarithmic to start with, they're actually super easy to convert to exponential form. So the way that I say to convert them is go around the globe starting with the base. So you have a to the 5th equals 4. Okay, now that's in exponential form. For b, we have log base e of b equals 3. So if you follow that same logic, you're going to go around the world. So e to the 3rd power equals b. Oops. E to the 3rd power equals b. And then if we do c, we have log base 3 of 5 equals c. So if you go around the world, 3 to the c equals 5. Okay, and you've just converted those from log form to exponential form. All right, let's look at a different set of examples. So in these examples, they want us to find the exact value of these expressions. Okay, So this is one of those examples where it's easier to convert your log statements to exponential statements because we're more accustomed to solving expressions if they're written exponentially than we would be if they're written in their log form. So what we can do to solve these, we want to know what their exact value is, so I'm going to say it's equal to y. Okay, I put a variable there. And now I'm going to convert this to an exponential statement. So we just learned to convert those. It would be 2 to the y equals 16. Okay. All right. So now this is an exponential equation that we can solve. We learned that if we're solving exponential equations, if we're solving for the variable, we have this rule. A to the u equals a to the v if u equals v. So the only way we can do that is if we can get the bases to be the same on both sides of our expression. Well, our base on the left-hand side is 2. And we would ask ourselves, well, can we write 16 using a base of 2, which is, can 2 be raised to some power that will give us 16? And yes, 2 to the 4th power. Okay. Since the bases are the same on both sides, we can drop the bases and set their powers equal to each other. So y equals 4. So that's the exact value. So log base 2 of 16 equals 4. That's what it equals. So anytime you're answering a log statement, you're actually saying, okay, this log base 2 raised to what power would give me 16? So the answer to a log question, if you want to think about it, is what is the exponent that makes this true? Okay. Anytime you are answering an exponential form, you're saying this base raised to this power gives me this answer. Okay. So same information, just in a different order. All right, let's try B. So we're going to do the same thing. We're going to set it equal to y. And we're going to convert this to an exponential statement. So we're going to say the base to the answer gives us the argument. So if I write that, that's 3 to the y equals 1 over 27. Okay, we're going to use that rule again if we're solving exponential equations. So we need the base to be the same on both sides of the equation. So the first thing I'm going to do, I'm going to fix this 1 over 27. So this is 3 to the y equals, all right. Now, is there a way that I can make 27 by raising some number to a power? I can. 3 raised to the 3rd power gives me 27. And you have a rule of exponents that says if you have a to the negative n, you can make it that exponent positive by changing the levels. Okay. That works in reverse too. So I can put it as a negative exponent instead of writing it as a fraction. So I'm going to say 3 to the y equals 3 to the negative 3rd power. Okay, now that my bases are the same, I can drop my bases and set my exponents equal to each other. And my answer is -3. Cool.